Okay guys, so if you follow along in your packet and take notes on this free response question, it's really going to help you out on one of the free responses tomorrow. So feel free to pause the video and take notes, try and work ahead, come back and check your work, all those good things so that you're preparing for your test. Let's read the problem. When a course ends, students start to forget the material they've learned. That sounds familiar. Let's let R of t be the percent of material that students remember after a certain time in months since the course has ended. A particular model for a group of students has the function R satisfying the following differential equation. When the course just ended at time t equals 0, the amount of material remembered is 100%, or R of 0 equals 100. Use a tangent line to the graph of R at t equals 0 to estimate the percent of material remembered after 0.5 months. All right, so I see that I'm being asked for a tangent line here at t equals 0. So what we know from prior units is that to find a tangent line approximation, I need a slope and I need a point of tangency, which I'll just abbreviate with point for today. The point of tangency here is going to be anchored at a t value of 0, since that's what I annotated up there. And I do need to investigate to find the y-coordinate of that point of tangency. But if you notice what I highlighted, at 0, students remember 100% of the material. So my point of tangency I can sum up at 0, 100. Slope. We have to try to remember this, guys. This is super important. Anytime you're interested in calculating a slope, whether that's on a slope field or in a tangent line equation or whatever, we have to make sure we're linking that back to our derivative formula. That's going to be how we're able to compute slopes at different points. So my slope here I can find by simply computing -1/4 of r minus 20. And R in this example is how much material I'm retaining at this point of tangency. So at time 0, I have 100% of that info stored in my brain. I do a little bit of simplifying. Let me see, 100 minus 20 is 80. So -1/4 of 80. I do a little bit of math. 1/4 of 80 is 20, and my 20 is negative. Forgive my bad handwriting. I'm having a hard time writing on my screen. So with that info, I have a slope, I have a point. My point of tangency and my slope allow me to create my tangent line equation, which is y equals -20 of t, I'll use correct variables here, minus 0 plus 100. Perfect equation of a tangent line, which I'm then asked, if I go back to the problem, I'm asked to use that line to estimate the percentage of material that's remembered after 0.5 months. So I can come back here and say, well, my estimated material here that I've internalized is approximately -20 of 0.5 minus 0 plus 100. All we have to do there is take our tangent line that we just created and substitute in the value 0.5. Sorry, that's a decimal right there, which allows me to get my estimate. Okay, I'm ready to move on to part B now, which you can see asks us for the double derivative of our original differential equation in terms of R. We talked about this a little bit in class today, so I'm going to elaborate. If I have a first derivative established for me here, and I want to find the double, what I'm required to do here is differentiate the first derivative. So I'm going to try to take the derivative of that expression that I see right there. Well, that's not hard for this first piece. The first derivative is here for me, dr dt. So if I want to differentiate that first derivative, that's what allows me to get to my double derivative notation. You can think about your stairs. We're just moving down one step. After a first derivative is a double derivative. This is going to be the harder piece. What I want to do now is differentiate the other side of the expression. which if I clean it up a little bit is negative 1/4 r plus 5. Hopefully you can follow where that plus 5 comes from when I distribute my negative 1/4 to the negative 20. So now I'm going to say, all right, well, my double derivative is equal to this derivative over here on the right side. The derivative of negative 1/4 r is negative 1/4. Let me switch colors so this stands out, times dr dt. The derivative of r with respect to time here is what I'm trying to capture. Plus, well, the derivative of 5 with respect to time is just 0, so nothing special there. The question asked me to record this in terms of r. Currently I'm close, but my simplified derivative is not in terms of r, it's in terms of dr dt. So to finish, I'll remember what the original problem was telling me, and in place of that dr dt, I'll use what I know dr dt is equal to and substitute that in to get to my actual double derivative in terms of r that's being requested. Okay, and now I finally made it to the last part of the problem, which is where all the good stuff comes into play. We are asked to find the particular solution to this differential equation with the initial condition r of 0 is 100. So this is really what we've been working toward this whole unit. First move, I hope makes sense to you. I'm going to take dr dt equal to all this stuff, but I'm going to go ahead and move the dt over to the other side, and then I will divide that r minus 20 to get that on the side with my dr variable over here. So this is putting me in a good place to hopefully attempt to be successful in this problem. After the separating comes the integrating, so I can tack on some integrals onto both sides and then think critically through this antiderivative process. You're kind of used to this by now, guys. 1 over r minus 20 had to have come from the natural log function. That's the only function that we know of whose derivative results in that reciprocal. So that one's pretty standard. And over here I have a negative 1/4 t plus c. So that's going to help me to anti-differentiate both sides. My job is to find my particular solution, which involves solving for r. So I'm going to exponentiate both sides on my next line, leading me to cancel those and be left with the absolute value of r minus 20 equals, big important thing here, e to that constant results in the super constant out front of the e to the negative 1/4 t. That's a super important step here that allows us to continue solving. Let me scroll over and pick up where I left off up here. I'm going to drop the absolute value bars, and that results in a plus or minus big C e to the negative 1/4 t. I'll choose my sign by referring back to my initial condition. It's positive, so I'll keep the positive as well. And I finally get to my general solution of 20 plus C e to the negative 1/4 t. That's close to what I want, but I was specifically asked to find a particular solution, not a general. So that means I'll plug in my initial condition of 100 for the r value with 0 plugged in for the t value. And you can see that lined up right here. Remember, you can do a whole lot of math, but I would prefer that you just simplify this down and get to an expression that you can reason your way through without having to do too much algebra. This is 100 equals 20 plus c e to the 0, and e to the 0 is 1. So I just get 20 plus c on the right-hand side here. So I'm asking myself, what does c have to be? And the only possibility is 80. So my particular solution is r equals 20 plus 80 e to the negative 1/4 t. successful particular solution, and I'm done.